Hello, I'm Dr. Maurice Dupree, and in this section we're going to discuss volume, the shell method. One way to get a volume of revolution is by viewing the volume of revolution as the result of sweeping out disks. If this is the axis at which we're revolving around, a horizontal radial line perpendicular to this axis of rotation, as it rotates, sweeps out a disk of a certain radius, and so then we calculate the area of the disk in effect and integrate that, which gave us an expression like pi times f of x squared. But another way to do it is to view the volume of revolution as being composed of the result of sweeping out by segments that are parallel to the axis of rotation. If I take a segment, imagine the marker here as a segment, and I rotate that around my finger, notice it sweeps out a cylinder. And so this leads to sometimes what's called the method of cylindrical shells, or for short, the shell method. So here in this picture, what I've indicated is the graph of a function y equal f of x here. It's a little curve, and that's the curve between x equal a and x equal b. And cross-hatched there is the region under that graph. And if we rotate that about the line x equals c, that sweeps out a solid volume of revolution, which I've sort of indicated here with the blue-green. Notice it'll have a kind of a shape to the top of it, and the outside here at x equal b will generate a cylinder whose radius from the axis is b minus c. Now, notice if I view this cylindrical object as composed of the results of revolving the little thin strips that make up this area under the curve that are vertical and parallel to the axis of rotation. And if I take one of these at, say, the location x, and it extends from the x-axis up to f of x, so its height is f of x. If I revolve that around the rotation axis, notice it sweeps out a cylinder, and we can think of that cylinder as having a certain thickness, the thickness of the little segment there. It's got a thickness, and so that swept out a certain volume, and that volume is like a shell in a cylindrical shape. In more detail, look at it right here. Its height is f of x. Here's the axis of rotation, and the radius of that cylinder, call it little r, characterizes it together with the height so that we can compute its volume. And the volume is simply the surface area times the thickness. Well, what is that radius? Remember, the axis of rotation is x equals c, and so if I'm out here at x, the difference here is the absolute value of x minus c. So consequently, what would the volume of the shell be? 2 pi times absolute value of x minus c, that's 2 pi r. That's the circumference of the cylindrical shell. If you multiply the circumference of a cylinder by its height, f of x in this case, what we then have is the area of the cylindrical shell, and then multiplying by its thickness, we get the little bit of volume that that shell has. And so integrating that from A to B all the way across gives us the total volume of that solid of revolution. Now, here's one thing to keep in mind. You don't want to deal with the absolute value of x minus c. So what you need to do is look at the position of the rotation axis relative to the region. In this case, for instance, as I've drawn it here, the region is to the right of x equals c, and so in effect the absolute value of x minus c would be just x minus c itself. So it's useful in this situation, wherever possible, to position the region you're rotating to the right of the revolution axis so that you can eliminate a lot of these negative signs. Well, let's look at an example. In our first example, we want to find the volume swept out by revolving the region underneath the curve f of x equal x minus x squared plus 2 for 0 less than or equal to x less than or equal to 1, which I've drawn a little picture. Obviously, it's a downward parabola, the coefficient -1 of the x squared. And so there it's picture. Notice when x equals 1, we get the value 2, because 1 minus 1 squared is 0, and when x equals 0, we get 2. In other words, it's crossing here at height 2 when x equals 0 and x equals 1. And so there's the picture of the region, and we want to find the volume obtained by revolving that about the y-axis. So in this case, the c is 0, and we're just going to get the integral from 0 to 1 of 2 pi x times f of x, well, dx, of course. And let me just fix this. This is 2 pi x f of x dx, and of course that's 2 pi x times what is our f of x? It's x minus x squared plus 2 dx, and we're integrating from 0 to 1. So there it is. Now the first thing to do is simply take the 2 pi outside the integral and multiply the x through and distribute it through. And so then we would get that our volume is 2 pi times the integral from 0 to 1 of x squared minus x cubed plus 2x dx. So now we just anti-differentiate. Antiderivative of x squared is x cubed over 3, minus antiderivative of x cubed is x to the 4th over 4, plus antiderivative of 2x is x squared, and that's to be evaluated between the limits 0 and 1. So when I put x equal 1, I get a third minus a fourth plus 1, and of course subtracting what I get by putting in 0, that'll be 0. And so that's our answer, 2 pi times the quantity a third minus a fourth plus 1. Now we can simplify this easily. A third minus a fourth is a 12th. A 12th plus 1 is 13 twelfths. 2 cancels with 12, and we get simply 13 over 6 pi. If we calculate that, what we'll find is it's approximately 6.807, and that's giving us the volume of revolution obtained by revolving this little region here under the curve x minus x squared plus 2 between 0 and 1 about the y-axis. Yeah, so in other words, it's going to look something like this. And it's solid, except that it's got this cylindrical right here. It's only curved right here at the top all the way around. Okay, so that volume is about 6.807 by the method of cylindrical shells. Now let's look at an example involving a bell-shaped curve. Find the volume obtained by revolving the region under y equal e to the negative x squared for x between 1 and capital R about the y-axis, and here capital R is just a number bigger than 1. Well, I've shown the graph of e to the negative x squared, y equal e to the negative x squared here, and you can see clearly that the exponent is always negative no matter what x is, and so consequently the maximum value is obtained when x equals 0. That's simply e to the 0 or 1. So there we are at x equals 0 at height 1. On the other hand, when x equals 1, our lower limit, we get e to the negative 1 squared, which is simply 1 over e. So here at x equals 1, the height of our curve is dropped down to 1 over e, and then of course as we go out farther it just gets lower in either direction. It's symmetric. So notice as I revolve this around the y-axis, this region here gets revolved around as it passes by the negative x-axis. It's going to look exactly like this region under the curve from negative r to negative 1. And notice it's making a kind of a sort of a hat shaped with it's nothing in the middle. The center is gone, and its vertical sides are pretty small here at the outer edge, if r is appreciable, because the height will just be e to the negative capital R squared. So there's a rough picture of it, and so we want to find the volume of it. Well, remember, the thing we're going to integrate is 2 pi x e to the negative x squared. Notice if I want to find the antiderivative of e to the negative x squared, I'm in deep trouble. There's nothing that we can do to anti-differentiate that in what's called closed form. It doesn't have a formula for its antiderivative. But as soon as I get that factor of x in front that the shell method gives me, that'll allow me to reduce this integral by substitution. So the volume by the shell method is 2 pi integral 1 to capital R of x e to the negative x squared dx. And so we simply do a substitution. We'll substitute u equal x squared, then du is 2x dx. Here's a 2 right here. So if I imagine putting this 2 in front of the dx, that would cancel it off the front. And here, 2x dx is du. So we have pi times the integral of e to the negative x squared is u. So we just get e to the negative u du. And what about our limits? Well, when x is 1, u is 1 squared, which is still 1. When x is capital R, u is capital R squared. So now we have a simple integral to do, e to the negative u du from limits 1 to r squared. Well, the antiderivative of e to the negative u is the negative of e to the negative u. And so that's to be evaluated from 1 to capital R squared. Now we can get rid of the negative sign here by flipping the limits of integration to simplify and make it less likely to make a simple sign mistake. And so now I just have to put in the upper limit 1, so that's e to the negative 1, or 1 over e, minus what I get by putting in the lower limit. Well, that's e to the negative r squared, or 1 over e to the r squared. And so there's our volume from 1 out to r of the region swept out by that revolving around the y-axis. What would have happened if I had replaced this 1 by 0? Let's come back here and look at the picture. What would I get if I revolved this whole region under the y-axis, to the right of the y-axis out to capital R, about the y-axis? That would give me the volume of this entire kind of hat-shaped figure. It would be the same exact integral, except now instead of going from 1 to r, I would replace this 1 by a 0. And so this 1 would be a 0. This 1 would be a 0. This 1 would be a 0. And instead of getting 1 over e here, we would have e to the negative 0, which is simply 1. In other words, that would wipe this out. And let me replace it by just the number 1. And we have pi times the quantity 1 minus 1 over e to the r squared for the volume of this whole hat-shaped figure out to radius r that we get by sweeping out as we revolve around the y-axis. Now let's use the shell method to find the volume of a donut. Here I'm standing in front of a big donut. Now let's look at it more closely. This donut is the result of revolving this region around the axis x equals c. And in order to make the equation of this disk simple that I'm going to revolve to sweep out the donut, I've centered the disk at the origin. So its equation is x squared plus y squared equal capital R squared, where r is the radius of this disk. And so consequently, the upper half semicircle has equation y equals square root of capital R squared minus x squared. And of course, the range of values here is simply from negative capital R to positive capital R. And so we're revolving this around the vertical axis at x equals c, where c is to the right. So c is positive. Now, notice that we have symmetry for the disk about the x-axis. So consequently, we can see that what happens when I revolve the upper half disk, this upper semicircle, what's under it, revolving that around the x-axis, around the x equals c, gives half of the volume of the donut. So I can simply use my shell method formula on the top half and multiply by 2. Well, my formula says the volume for what's under the upper half, what that sweeps out, is 2 pi integral negative capital R to capital R, absolute value of x minus c times the square root of r squared minus x squared. And so I'm doubling that, and this gives the volume of the entire donut. So we've built in some symmetry. We also notice have some symmetry here because we're going from negative r to r, and there's a certain symmetries in that integrand. So let's look at that a little more closely. In the first place, and before I go over, notice that since c is to the right of the disk, for any x in the disk, the absolute value of x minus c is c minus x. So because of that, over this region negative r to r, the absolute value term is going to be replaced by simply c minus x. So consequently, our volume is 2 times 2 pi integral negative r to capital R, negative capital R to capital R of the quantity c minus x times a radical capital R squared minus x squared dx. Now, the first thing to do is break this into two terms. So the first term will be c times the radical, and the c comes out. So v equals 2 times 2 pi c times the integral from negative capital R to capital R, square root r squared minus x squared dx. And what's the second term? That's negative 2 times 2 pi integral negative capital R to capital R x times square root r squared minus x squared dx. And so that's all we have to work out. Now, the first thing I'm going to do is notice that if I take this 2, put it here in front, so cross it off from there, put it here in front, what does that represent? Remember, when I integrate negative capital R to capital R of square root r squared minus x squared, that gives me the area of the upper half of the disk, and so multiplying it by 2 gives me the area of the disk of radius capital R. So we know what that is. That's pi capital R squared. So we get for the first term 2 pi times the c times pi capital R squared. How about the second term? Well, let's look at this integrand. We could go through some substitutions and so forth and simplify it, but let's use what we know about odd and even functions. Here, this factor is certainly even. Replacing x by negative x does nothing to it. On the other hand, that factor is obviously odd. If I replace x by negative x, it changes the sign. So in effect, whatever this looks like, we know that to the right of the axis is just the same as to the left, except upside down. It looks something like that. Consequently, when I integrate it from negative r to capital R, this part of the integral will cancel that, and this quantity has to be completely 0. In other words, that entire integral is equal to 0 just because we're integrating an odd function from limits negative capital R to capital R. And so what are we left with then? Our volume is equal to 2 pi little c times pi times capital R squared. You might notice, if we come back to our picture here, that when I revolve this disk about the axis x equals c, if I look at the center of the disk, where did it go? it revolved all the way around, creating a circle of radius c. That circle has radius c, and so what's the circumference of that circle? It's 2 pi times little c. 2 pi little c is the circumference. In effect, under the rotation about the axis, the center of the disk traveled that distance. And so what we're finding is that the volume of the donut is simply the distance that the center of the disk traveled multiplied by the area of the disk itself, which is a very nice simple result and a simple way to remember how to find the volume of a donut. Just take, in effect, the distance that the center has to move to go around its axis of symmetry, multiply by the cross-section area of the donut, and you have it. Well, we've worked some problems with the shell method. Now you should try some on your own for practice.